So the title of this module is Interpolation and Curve Fitting. And let me give you a brief background on this. So interpolation is a method of constructing new data points within the range of a discrete set of known data points. So basically, if you have points, I'm going to use different color. Let's say you have some experimental values here, here, and here. And then basically interpolation is creating a figure, a curve, a function that touches upon all these points. And in that case, you can so-called interpolate the value of the function at other points beyond the range of given data points. Okay, there are several ways to interpolate. The simplest one is called nearest neighbor interpolation. So in that case, if you have these data points, let's say, what that does is it draws a constant, it keeps the function constant until the midpoint between 2 points, and then it breaks up and then goes all the way to the value of at the next point, and then holds it until the midpoint between 2 other points. So this is nearest neighbor interpolation. Of course, it's not the most realistic interpolation. Sometimes a simpler version of this would be called the linear interpolation, when you connect the dots using the linear functions in between. So it would just go like this. There is more smooth version of interpolation. It's called, actually let me call this linear interpolation. There is more smooth version of this. It's called polynomial interpolation. When for the set of n data points, you choose the n-1 degree polynomial to fit all these points and plot the curve that passes through all of these points. This would look something like this. An even smoother version of interpolation is called spline interpolation. When you, in between the given data points, you construct individual polynomial functions of the order of 3 or greater. So those are going to be the polynomials of the order 3 or larger in between each point. And that way, you can prove mathematically you would minimize the error. So if you need more precise fitting, then you would use splines. Okay, the most popular spline interpolation is the cubic interpolation, but the order can go high. So in that case, it would be much smoother and much more close to the true values of the data points, so that would minimize the error. So let me show you how MATLAB handles this for the function of one variable, and then we'll talk about interpolation for the function of 2 variables. Okay. So interpolation, one-dimensional interpolation. So suppose you have the data, but let's say it could be measurements of from your experiment. You have x values on the x-axis and the corresponding values on the y-axis. Okay, so it's basically a one-dimensional function. Those are given data points. Then let's say you would like to evaluate the value of the function in the points in between. So you can see those points on the x-axis are given kind of arbitrarily or whenever your experimental values lay, and you would like to interpolate this on the range between -20 and 20 in the with the step size of 1. Again, everything is custom defined. It could be from -10 to +10 with the different size and so on. So you would like to interpolate the value of the function at these points. Okay, so there is a simple command called interp1. 1 pertains to the one-dimensional function. You submit the given data points x and y, and then you submit the points in which you would like to interpolate the value of the function. We call them xq. And then you can plot. Okay, you're going to plot. I'm going to plot the data points x, y, and I'm going to use the circle to mark them. And then I'm going to plot the interpolated value of an interpolated plot. The default interpolation is linear interpolation. So I'm going to plot them at the points where I interpolated the value of the function. So xq, yq. And I add a little twist to this. I'm going to use the dotted line, dotted and dashed line. So if you run MATLAB, okay, so like I said, the default interpolation is the linear interpolation. So the circled points are the points with the given data values, and in between we have the interpolation. A different type of interpolation is spline. So you can do that. So you can see it's much smoother. A more rough interpolation is, as I said, nearest neighbor in the beginning. So on the figure 3, you can see that it holds the constant value that corresponds to the first given value, and then it breaks down to it holds it until the midway between two given points, and then it breaks it down to another given value. But this is a rough interpolation. Cubic spline interpolation. It looks very similar to the spline interpolation, but spline interpolation, if you choose spline interpolation, like here, MATLAB picks out the polynomials in between the given data points itself. Here, you kind of force the MATLAB to choose cubic interpolation, meaning the cubic polynomial is going to connect every two given data points. You can also, if you would like to, having plotted the interpolated plot, you can also obtain the value of the interpolated value in the points that are outside of the given range of points. So let's say you would like, so your range of points is here, and for each of those points you have the values of the function, but what if you would like to estimate the value of the function at x equal to 0.25? You invoke the same command, interp1, given data points, and then you submit the value x, which is equal to 0.25, and MATLAB will give you the value of the function at that point. So at that point, the value of the function is 8.71. And for that, I'm using cubic interpolation. Okay. In a similar fashion, you do the interpolation of a two-dimensional function. You define the so-called mesh grid. So it's going to be the given points on the x-axis and given points on the y-axis. So keep in mind the two-dimensional function is the function of x and y. So you need to submit both x and y values in order to get the z value. The z value is the value of the function. So it's going to be a three-dimensional plot. So I'm on the x-axis, my given data points go from -2 to 2 with the step of 0.5. you can define it any way you want. Let's say you can define a vector x that contains given values of x. You can define vector y that contains given values of y, and then you submit them here. So instead of this, you will have x, and instead of this, you will have y. It's totally custom defined. And the value of the function, you need to give the value of the function. I picked this function just out of blue, and we'll work with this function, but if you deal with experiments, sometimes you just have that value of the function v given as a matrix. I will show you how to do this, how to define the function as a matrix at the very end, but for now let's work with these numbers. So this is the function, and I would like to interpolate. So I'm given the value of the function at these points, and I would like to interpolate. Interpolate on a slightly different plot, on a slightly different set of points. So I define another mesh grid with let's say a smaller step. So it goes from -2 to 2 on x-axis, but instead of step 0.5, I do step 0.1. And from -4 to 4 on the y-axis with the step of 0.1 as well. So those are my new points in which I would like to interpolate the value of the function. And the same command, similar command, interp2, because we're dealing with the function of two variables. I submit the values of my arguments, x and y, submit the value of the function, and then submit the set of parameters or the arguments at which I would like to evaluate the function, interpolate the value of the function. And that's it. So you collect the values of the function at the interpolated points, and then you can plot a new plot. Okay, so it's going to be xq, yq, and vq. Remember the two-dimensional plot, you can plot in several different ways, but one of the commands is surf. So you need to submit the x and y values, and then the value of the function itself. So let me comment out everything else and plot what we have just discussed. All right, so one more time. So this first plot on figure 1 is the plot of the function with the given data points, no interpolation. Actually, MATLAB does a default linear interpolation on this plot. What you see on the second plot is with the reduced step size of 0.1 instead of 0.5, and a default interpolation method is the linear interpolation. That's what it looks like. The next would be spline interpolation, so you will see a much smoother plot. Okay. You can also, if you'd like to extract the value of the function at some given point, you can do that just like we did with the one-dimensional plot. Here you can interpolate the value of v at a specified point. Let's say I pick the specified point x equal to 1, y equal to 0. So you type interp2. You need to submit all the data, all the given data, x, y, and v. Those are given data, and then you need to submit the point. And the type of interpolation that you would like to use for this estimation. Let's say spline, or could be linear, or if you don't put anything, MATLAB is going to use the default linear interpolation method. So if you do that, MATLAB will give you the value of the function. So it's 0.3679. And the last thing I want to show you is how to do this using nearest neighbor interpolation. So you can see this is a very rough plot compared to the other ones. Finally, I want to show you how to. So you can do everything we've done so far, but with the function v defined as a matrix rather than a given function. Because sometimes for the measurements in the experiments, you get the value of x, you get the value of y, and then you get a specific value of the function. So and then you can put these values of the function in a matrix. So let's say I define a mesh grid for, so x runs from -1 to 1 with the step 1. So I'm going to have 3 points on x-axis, -1, 0, and 1. And same thing on the y-axis, -1, 0, and 1. So I'm going to have a total of 9 values of the function, right? If you have a grid of 3 points on x-axis and 3 points on y-axis, I'm going to have 9 values of v. So it's going to be, v is going to be defined as a 3 by 3 matrix. That's what I do. And I picked out just arbitrary numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So the point of this is to show you that v could be defined manually as a matrix as opposed to v being defined as a function. So in case you don't know what the function looks like, but you have the values, you can do that as well. So just define v as through a matrix. Same thing, you define another mesh grid with a smaller granulation. Invoke the command interp2 and submit the values of the given points, given values of the function, and points where you would like to interpolate. And that's it. You collect the values of the function at those interpolated points, and then you plot the interpolated graph. So the last plot here will be the interpolated graph. This is going to be, obviously this graph is going to be different because before we interpolated a given function here, those are just arbitrary values that I picked. So 1, 2, 3, 4, 5, and so on. So that's what it looks like. But technically, this is the point that I wanted to bring to you, is that you can always do that. Okay, curve fitting. So curve fitting is basically a procedure of fitting the best curve for the given data points. Let me just briefly show you what that looks like. In fact, even though it's seemingly different from interpolation, because in the interpolation the curve must pass through each point. Here, let's say you have several data points. And you try to fit the best curve in a sense that the square of the error between this curve and the given data points is minimized. Okay, so this would be the curve fitting. Believe it or not, but interpolation is a special case of curve fitting. So let me show you how to handle this in MATLAB. Let's say you have a given data points in some Excel file. You can define those data points manually. You can define, let's say, X values in the array and Y values in the array. But I wanted to show you how to extract the values from a given Excel file. So I have the Excel file here. If you can see it, I can open it. Okay, so this is the given Excel file. That's how MATLAB opens it up. I wasn't too innovative. So on X-axis I have 1, 2, 3, 4, 5 up to 20, and on the Y-axis I have some values. So I'm reading this data. So there's a command in MATLAB called XLS read. So I'm going to read the Excel file, and you give the name of the Excel file. And then you need to basically identify the columns in this data file. So I define my X as data, as the first column of the matrix data, and my Y values as the second column of the matrix data. And I write here in the comment that alternatively you can introduce this data manually. So you can define an array X equals 1, 2, 3, and Y equals whatever. But make sure you introduce them as vectors, not rows. So first thing, let's say we just plot those values on the plot. See what they look like, and then just the bare look of the plot will give you an idea of what kind of curve fitting, what kind of curve would be the best fit. I mean, this looks like a linear to me. But there could be variations. So let's try first. Let's try the linear curve fitting. So I'm going to try to find the best linear function that suits this data points. So this is done by the command called fit. First you introduce the given values, and then you introduce the default in MATLAB embedded curve fitting technique. So when you say poly 1, that means that MATLAB is going to invoke a polynomial of the first order, which means that ax plus b, and is going to find the best values of a and b to fit these data points. And once we do that, so let me uncomment the whole thing. What happened here? Ah. How do I undo this? Oh, okay. Okay. So first of all, so these are the given data points. Then MATLAB has calculated the parameters of the linear curve, those A and B. MATLAB calls them P1 and P2. So this is the linear model. And MATLAB gives you the values of the calculated best values for P1 and P2. Okay, and that's what it looks like. Okay, so for the given data points, MATLAB gives you the curve that passes through these points. Okay. All right. So the syntax of this is the following. So you plot, you type up plot, then you put the f, which is the function that you're trying to fit, and then the x and y values for which are the given data points. So that way MATLAB will show you all the points on the curve. So you're going to have both given data points and then the plot of the fitted curve. Okay. Next, what you can do is custom curve fitting. So let's say you don't want linear interpolation. You want something else. You can do that as well. So you type up the same thing, fit, and submit the given data, x and y, and then let's say I would like to curve fit the exponential function, a times e to the power of bx plus c. And MATLAB will select these three parameters, a, b, and c, in order that best fit the given data. Okay? So, and then you plot the same in the same fashion as we did before. So first of all, MATLAB will give you the parameters of this exponential function. So if you look at the command window, MATLAB generated the function a times e to the power of bx plus c and gives you the best fit parameters a, for b, and for c. Okay? And then the plot will look very much the same, but you can see there is a little bending because it's not a straight line, it's an exponential function. But the two plots will look very similar. So so the plot on figure 2 is the linear curve fit, and the plot on figure 3 is the exponential curve fit. The plot on the left is straight line, it's supposed to be. The plot on the right is an exponential function. You can see a little bending in the graph on the right. Okay. And like I said earlier, interpolation is the special case of curve fitting. So you can actually do the curve fitting here as well. So it's done by the same command fit, even though curve fitting was the subject of the even though interpolation was the subject of the previous two files that I showed you, you can do the same thing here. You can do fit in the cubic interpolation, cubic interp. There is a special string that you need to include into the command feed, and MATLAB will plot this interpolated plot. Again, it's probably not what you want when you do the curve fitting, but just to show you that interpolation is a special case of curve fitting, you can do that. Basically, that's it. That completes this module. Done.